In this video, we're going to take a look at the Diels-Alder reaction and its regiochemistry and stereochemistry. Where do all the pieces go when we're all done? Let's jump right in. Let's look at this example. My dienophile, this alkene, has two carbonyl groups that are cis to each other. They're on the same side of the double bond. So if I draw in the hydrogens, they're like this. When this zips up, all of these bonds are formed at the exact same time. So we form our six-membered ring, and on these two carbons right here are where these carbonyl groups are. But the question is, are they on the same side of this ring, or are they double, or on the? But the question is, are they on the same side of the ring, or are they on? But the question is, are they on the same side of the ring, or are they on opposite sides of the ring? And since they started off on the same side of the double bond, in the end, they need to be on the same side of the ring. So maybe they're both wedges, or they're both dashes coming in front of, or in this case behind the ring, but they have to be on the same side if they start on the same side. Conversely, if I started with a trans compound, when it zips up, zip, 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 we'll make my six-membered ring. In this case, these need to be on opposite sides of the ring from each other. So one's a wedge, one's a dash. Or it could be the opposite way. But they have to be on opposite sides if they start on opposite sides. And they end up on the same side if they start on the same side. So we call double bonds that are on the same side of a sigma bond S-cis. They're cis about this sigma bond. And these would be trans on this single bond or sigma bond. So we call those S-trans. And our diene needs to be S-cis in order for the reaction to happen, because they both need to be on the same side in order for me to zip all the way around to make my final product. So that means compounds that start off forcing those to be S-cis may be something like this, that would link these together. Now they can't rotate trans. That kind of compound could zip up and make our final product. It would look something like this. Let me help you see this better. So let me start with this. Let me take this point and just push it up higher. Then I react with my double bond. Zip, zip, zip. And that makes this, which is the same thing as that, a bicyclo compound. So we like these to be on the same side. Groups that make it difficult for those to be on the same side, maybe if there's like some big methyl groups like this, and these would start to bump into each other, this would not want to be S-cis, and it probably would not do a Diels-Alder reaction. So let's analyze this Diels-Alder reaction. I can take these electrons on the methoxy, start to push them into the ring. My diene likes to be electron rich. And I can see if I push those electrons, I can keep pushing, and I can get a resonance form. I can push those electrons in, and I can get a resonance form where this carbon atom is very negative on my diene. On my dienophile, I can take these electrons away from the alkene of the dienophile and push them all the way onto this nitrogen. That would make since I removed the electrons from this carbon, I have a positive on this bottom carbon. And this positive and negative like to get together, opposites attract. So they would get in this form in order to zip up and make my final product. If this is the most negative carbon, and this is the most positive carbon, we would not want to line it up with my most negative carbon opposite my most positive carbon. So this would not zip up my Diels-Alder this way. We get them close together like this first. So I like to make 1, 2 and not 1, 3. So let's analyze this reaction to see what we think would happen. Well, let's take these electrons and see where we can push them. If I push them in, I can't push down to here or I break my only single bond. So I guess I'm going to push those there for the most negative spot. So this carbon is the most negative carbon. Let's see, if I try to push the electrons away, I can go up to the oxygen this way. So this carbon on the bottom is my positive carbon. So are these two getting together if I line them up this way? No, they are not. So I will not make this compound. Instead, I think I want to redraw this. This is the most negative spot. So I'm going to flip this one over because this is the most positive spot. My positive and negative get together. I zip, zip, zip. So instead of 1, 3, I don't make that. I like to make 1, 4, where those are on opposite sides of each other. So I like to make 1, 2 or 1, 4, but not 1, 3 in either case. And the reasoning behind it is the most negative spot gets together with the most positive spot. Hey, look at this next video and you'll learn more about some of the other details behind the Diels-Alder reaction, but I didn't want this video to be too long. Please subscribe so I can continue to help you with your organic chemistry.